Good morning, students. In the previous classes, you studied about two terms. One is electric potential and potential difference. Then also you studied about equipotential surfaces. So today we are going to find electric potential at any point due to an electric dipole. You are familiar with the term electric dipole. Di means two. Pole means poles, polarity. Which are the two polarities? Minus and plus. So, minus q and plus q separated by a distance 2a constitute an electric dipole. That is what you studied in the previous chapter. So, equal and opposite charges located at two different points. That is a simple language. Equal and opposite charges located at two different points will constitute an electric dipole. The length of the dipole 2a is a vector quantity and the direction of that vector is from minus charge to plus charge. So that is this diagram. So AB is a dipole. Now P is any point which is at a distance r from the center of the dipole such that OP make angle theta with the length of the dipole. So which are the variables in this diagram? There are two variables. One is theta, another one is r. So different values of theta and r, you will get different points. So P is any point which is at a distance r from the center of the dipole such that OP make angle theta with AB. The construction in this diagram is there are two constructions. One is draw AM and BN perpendicular to PO. You can see BN perpendicular to PO and AM perpendicular to PO produced. These are the two constructions in the diagram. And this angle is theta, therefore vertically opposite angle. This one is also theta. Length 2a, that is why OA and OB both are A. Now what is our aim? We have to find electric potential at P, at any point P. Electric potential at P. So you know electric potential V is equal to KQ by R. That is what we proved in the previous classes. So to produce electric potential, what is required? You need a source charge. Distance of the point from the source charge is R, then potential of the point V is equal to K into source charge upon distance. For this point P, how many source charges are there in the diagram? There are, you can see, two source charges. One is minus Q, the other one is plus Q. So due to minus Q, there is potential at P. Due to plus Q also, there is potential at P. So potential at P due to A and potential at P due to B. You take the sum, you will get the total potential at the point P. So potential at any point P, VA plus VB. And VA means K into charge located at A, that is minus Q divided by the distance is AP. And for this one, KQ by BP. You can take KQ as common factor. So it will be 1 by BP minus 1 by AP. Now you see this triangle, either triangle AMO or triangle BNO. In both these triangles, you can see that angle M and angle N are 90 degree. Therefore, OA is the hypotenuse. So hypotenuse, length of the hypotenuse is A. And OM and ON are adjacent sides. So triangle cos, from triangle AMO, cos theta is equal to OM by OA. And OA is A. So OM you can write A cos theta. Similarly in this triangle, you can write ON also as A cos theta. Now see once again. Here see the diagram. If P is far away from O, P is a large distance from O, then your AP is approximately is equal to, what is AP approximately is equal to? PM. And the PM you can write PO plus OM. Right? And PO plus OM becomes R plus A cos theta. Similarly, the other distance, that is BP. BP is approximately is equal to NP. And NP you can write R plus A cos theta. You substitute these two. R plus A cos theta for AP and for BP and NP is R minus A cos theta. It's not R plus A cos theta, it is R minus A cos theta because NP is OP minus ON. OP minus ON. So it will be R minus A cos theta. You substitute both these terms in this expression. You are getting potential at P is equal to KQ. What is K? K is Coulomb constant. Bracket 1 by BP, meaning 1 by R minus A cos theta minus 1 by R plus A cos theta. Now take the LCM. So potential at P is equal to KQ. You can see that your LCM is R square minus A square cos square theta. Product of the denominator. And numerator will be R plus A cos theta minus of R minus A cos theta. You open the bracket. You can see that R and minus R cancel each other. And inside the bracket you will get 2A cos theta. You are familiar with the term dipole moment. P vector again. And dipole moment, you know, 2AQ. 2A is a vector. So 2AQ is dipole moment. The symbol for dipole moment is small letter p, small p, vector. So here you see 2AQ. This 2AQ is dipole moment. So the final expression will be K into, because 2AQ is K. 2AQ is P. So KP cos theta divided by R square minus A square cos square theta. This is the expression for potential at any point due to an electric dipole. Now, suppose the point is along the axial line. Suppose the point is along the axial line. P is any point on the axial line. Then what is theta? If P is along the axial line, then your theta is it 90 degree along the axial line? No. Along the axial line, theta is 0 degree or 180 degree. Theta is equal to 0 degree. Therefore, V axial is equal to, here instead of theta, you have to write 0 degree. So Kp into cos 0, that is cos 0, you know, that is 1, divided by R square minus S square. If theta is along the equatorial line, what is happening? If P is along the equatorial line, note 2, if P is any point along the equatorial line, then you know equatorial line on the dipole means that is a perpendicular bisector. If P is along the perpendicular bisector, then your theta is 90 degree, and you know cos 90 is equal to 0. So if you substitute here Kp into cos 90, Kp into 0. So V equatorial is equal to, numerator is 0, 0 by something, that is 0. So what is your conclusion? At any point along the equatorial plane, V means electric potential is 0 degree, 0. So V axial is Kp by R square minus A square, and V equatorial is 0, where P is equal to 2AQ. This P is 2AQ, small letter p, dipole moment. Based on this concept, suppose you are drawing or considering a plane passing through O, that is called equatorial plane. What is the potential at any point along the equatorial plane? We proved that it is 0. Therefore, equatorial plane, is it an equipotential surface? Because you know, a surface in which all the points have same potential is called equipotential surface. Along the equatorial plane, you can see that all the points have 0 potential. Therefore, equatorial plane is an equipotential surface. Thank you.